Force. I'm Tafarrat Babu. Today we are going to discuss about work, energy and power grade 11 concept that we have already previously started to discuss. So we have covered about the mathematical expression of work. Previously we have seen how to represent mathematically work, mechanical work. So work can be expressed as force dot S, dot product of two vectors. It can be expressed as Fs cosine of theta, where theta is the angle between the force and the displacement. The other points that we have seen was work done by constant force and work done by variable force. So there are force which are always constant due time and space, and there are force which varies with position. Therefore, among these forces, the constant force might be constant applied force. We might have a gravitational force and a frictional force. Whereas the variable force can be, a good example of variable force is spring. Then work done by the applied force, by a constant applied force, can be mathematically expressed as F dot S, which is Fs cos theta. Whereas work done by frictional force is a negative. Frictional force is always against the motion. Therefore, Fs is equals to the negative of Fs. Whereas work done by gravitational force is equals plus or minus. It can be plus or it can be minus mgh, which means as the object is moving upward, it is minus. As the object is moving downward, it's plus. So this was what we have previously discussed. The other point is the work done by variable force. So work done by variable force is work done by the spring. A good example of variable force is spring. And it can be mathematically given as the negative of half times k times x squared, where k is stiffness or force constant. Or it might be also known as force constant, spring constant, or stiffness. Graphical representation of work for a constant force is possible to have such a rectangular shape, which is the product of force and displacement is area. So the area gives us the work done by constant force. Whereas here we might have a different variable force, and in higher grades it's possible to use integral mathematics to find the work done or the area of such graphs. But here we are trying to see a very simple variable force, which is work due to spring force, and we have a linear variation between the force and the displacement. There is a linear variation, so that it's possible to have such a triangular expression. So this expression was determined from either triangular area or finding the average force, or it's possible to use integral, but it is more or less in higher physics concepts. Therefore, this was what we have previously seen. So today we'll try to see about work done by conservative and non-conservative force. We have to define what energy, list the different types of energies. We have to define what power is, and the other concept, we should have to solve some important problems concerning on work, energy and power. So let's try to discuss about work done by conservative and non-conservative force. The other name for non-conservative force is dissipative force. So what does it mean by dissipative force? Well, first let's try to see conservative force, then we'll try to see about non-conservative force. Conservative force are types of force in which the net work done is zero for a complete path. For example, if you take point A and B, the initial point and the final point, as the initial point A and final point B. So when work is performed from A to B and again from B to A, the net work done becomes zero. Okay? For such case, it's known as work done by conservative force. So the force is conservative if the net work done by such force is zero for a complete path. And the other point is work done by conservative force or such force are independent of the path. When you take from A to B, you might take different paths. It is independent of the path. When you come to that of a non-conservative force, whenever you take a complete path, the work rather be doubled. It's not cancel one another and becomes zero, rather it increases. Therefore, the work done for non-conservative force, the net work done for a complete path becomes double. and it depends on the path that we choose. Such forces are known as dissipative force or non-conservative force. An example of such force, conservative force, are gravitational force and work performed on a spring are considered to be the work done by conservative force, or such force are known as conservative force. The other force, non-conservative or dissipative force, are frictional force. Usually we can categorize all this under frictional force, but depending on the medium, we can take it as a damping force and dragging force. So let's take work done by gravitational force. For example, let's take here. Here we have point A. Here we do have point A, and here we do have point B, or it might be the ground. Suppose that the object is moving from A to B. So as the object is moving from A to B, it's possible to determine the work done. As it moves from A to B, it's possible to have the work done, and the work done from A to B. Previously, we have already discussed this point. The force is due to gravity. There is a downward force, which is mg. And the displacement S is the height from this to this. We can take it as h, cosine of theta, where theta is the angle between the force, which is mg, and the displacement S. Therefore, it is 0, cos 0. Therefore, mgh is the work done by the gravity as the object moves from A to B. Again, when work is performed from B to A in the reverse direction, if this object moves from B to A, which is against gravity, when it is moving upward, the displacement is upward, but the force is acting downward. Therefore, Fs cosine of theta, where mg is a force which is always acting downward, but h is the distance from this to this. Again, let it be h. Let's take it as h. So Fs cosine of theta, the angle between the force and the displacement. As the object is moving upward, the displacement is upward, but the force is acting downward. We have already previously discussed this one. The angle between the two is 180. Cosine of 180 is -1. Therefore, work done by gravity as the object is moving upward is negative. So let's take the net work done for a complete path. That means the work done from A to B plus the work done from B to A for such cases becomes 0. As the object is moving upward, it's negative. As the object is moving downward, it's positive. Therefore, when we add these two, mgh plus minus mgh gives us 0. So the net work done by complete path for a conservative force, like gravitational force in the spring force, becomes 0. It's also possible to take spring force. Now let's see. The work done by conservative force is independent of the path. We have said that independent of the path. What does it mean by independent of the path? It's possible to take this mass from point A to B. You can possibly take from A to B, or it's possible to take from A to C. There is a path. You can take this longer path or this path. Then let's try to determine the work done as this object is moving from A to B and this object moves from A to C. First, let's try to determine the work done as this object moves from A to B. If this object is moving like this, downward from A to B, the work performed by gravity is acting downward, which is mg. We'll use or try to determine the cos component, mg, cos theta. And we have height h. Here you do have h. Therefore, we have mg cos theta, this component, and downward force component, exactly like this, is mg. mg times h, we do have a force. mg cos theta is the force component perpendicular to the inclined surface, whereas the force component which is acting parallel to the surface is known as mg sin theta. The sine component is acting along the inclined plane, horizontal to the plane, and perpendicular to the plane is mg cos theta. But when this object is moving downward to this point, the only force acting is mg, and at this point we have a displacement of h. Therefore, work done from A to B becomes mg h. We have mg h. But when we take from A to C, let's take a distance from A to C. In this case, mg is acting downward. This definition is the basic definition of displacement. This theta doesn't mean this theta, okay? There are, theta can be interchangeably used, but in this case, theta, when we say theta, it is the angle between the force and the displacement. The force is mg, and the displacement is as well downward, so that we can take this theta as 0. That's why mgh is written there. And the other location, or the other displacement, is from A to C, the other path. So first, we just took and find the work of this mass from A to B as mgh. What if we took this object from A to C? Well, the work done from A to C is expressed as Fs cos theta. Well, the angle theta is always the angle between the force and the displacement. The force is acting in this direction. Which force? Well, mg sine theta, the sine component of the force. Mg sine theta is acting along the path. The displacement is as well on that path. Therefore, we can take that angle, the basic definition of work, theta, this theta might be differ from this theta. Therefore, it's possible to use just Fs. Then, the force is the horizontal component or the parallel component of mg, which is mg sine theta. Taking mg sine theta and the displacement s, it's possible to have mg sine theta is the force, mg sine theta times the displacement s. Now, students, let us take s sine theta. Let's interchangeable these two. What does it mean by s sine theta? In your mathematics lesson, it's possible to take sine and cosine. When we mean by sine, sine is opposite over hypotenuse. Therefore, sine theta is opposite h over hypotenuse s. Therefore, h is equals to s sine theta. When you crisscross, we can have s sine theta as h. Therefore, instead of writing sine theta, it's possible to resubstitute it as h. Therefore, we can find the same expression as that of this one, mgh, mgh. Then, whenever you take this object from this to this, it's mgh. Even though we take the same object on this path, it's also mgh. There is no difference. Therefore, it is independent of the path. Okay? You might take this path, you might take this path, or you might take a different zigzag path. It's independent. Therefore, work done by conservative force is always independent of the path. It only depends with initial and final location. Now let's see energy. In the case of dissipative force, if you take two paths, for example, work done by frictional force, whenever you take from A to B, you have some kind of value, and from B to A, we have the same value, but when you add these two, the value becomes doubled. It won't be cancelled out. Now let's see about energy. Students, what do you mean by energy? By the way, energy is one of the most entity or the most important part of the universe. Universe without energy is impossible. We have life exists in the universe due to energy, and energy sometimes it's an abstract term, but commonly used in science. Therefore, for literally defined work, energy, we should have to associate it with work. Therefore, energy is something which enables us to perform work. Whatsoever the type of the work, it can be electrical, it can be mechanical, it can be nuclear, or whatsoever, which enables us to perform work. Therefore, the ability or the capacity of something which enables us to perform work is known as energy. Energy in the universe exists in different forms. It exists in mechanical, nuclear, solar, chemical, and so on. Therefore, for this topic, we are trying to deal only the mechanical form of energies. Therefore, the mechanical form of energy, the two common mechanical form of energies are kinetic energy and potential energy. These are the concepts that we are trying to deal. So, students, from your previous concept, you have learned about kinetic energy and potential energy. Do you recall that kinetic energy is a type of energy due to motion, and potential energy is due to the change of position? I hope you do so. Therefore, let's try to discuss about kinetic energy and potential energy. Kinetic energy is the one form of mechanical energy, and it's energy due to motion. Suppose here, let's take a massive object M, a displacement of s from this point to this point. While it moves, its velocity might be changed from initial velocity to that of a final velocity. Now, from your previous concept or from your kinematics concept, you have defined that the final velocity squared is equals to the initial velocity squared plus 2as. From this, it's possible to resubstitute it as 2y of a times s. Then, at last, you can find this expression. Acceleration times displacement is equals to v final squared minus v initial squared over 2. Then, we have defined work. Previously, we have defined work as what? Work is equals to force times displacement. Therefore, when you substitute as work is equals to force times displacement. In this case, we have defined force as, in your previous unit, which is unit 4, you have defined that work can be, a force is equals to mass times acceleration. Therefore, mass times acceleration times displacement. Therefore, instead of acceleration and displacement, from the kinematics concept, you have this expression. When you substitute it here, you have that mass times acceleration times displacement equivalently substituted as 1 over 2 mv final squared minus 1 over 2 mv initial squared. This one is acceleration times s. This expression is acceleration times s. Then acceleration times s is already force times displacement, and force times displacement is known as work. And work is equals to 1 over 2 mv final squared minus 1 over 2 mv initial squared. So, the quantity on the right side enables us to perform mechanical work. And what is the quantity on the right side? It is something, this is a change of something which enables us to perform work. What is that? So, the quantity on the right side, which is the expression of half times m times v squared, is known as kinetic energy. Because kinetic energy is the one which enables us to perform work due to a difference in velocity. Mass remains constant, but here velocity change enables us to perform mechanical work. So the quantity on the right side of the equal sign is expressed as mv squared, is known as kinetic energy. So what is kinetic energy? Kinetic energy is energy due to speed or due to motion. And the other form of energy is potential energy. We'll try to deal with that. In this case, we have to discuss about work energy theorem. But before that, we should have to have exercise. And it's a time of activity. So students, can you try what is the kinetic energy possessed by a 4 kilogram object as its speed is exactly 6 meters per second? Please try that. Students, I hope you have tried this exercise. So, first, the quantities, the given quantities are 4 kilogram object, the mass of the object is 4 kilogram, and its speed is 6 meters per second, which is very simple and direct forward example or exercise. So, the kinetic energy, we have asked to find the kinetic energy. Therefore, kinetic energy is equals to half mv squared. When you substitute this, you can find it to be 72 joule. By the way, the SI unit of energy and the SI unit of work are all similar because energy enables us to perform work. Now let's see a very important theorem in this unit, which is known as work energy theorem. Work energy theorem tells us that the net work done on a given object is always equals to the change of the kinetic energy. For a given object, the change of the kinetic energy is equals to work. This is what you call work energy principle, sometimes known as work energy principle or work energy theorem. It's a very, very important theorem. We'll try to deal with that later. So let's try add some additional problem. What is the final speed of a 4 kilogram object if its initial speed is 2 meters per second as 42 joule of mechanical work is performed on it? Suppose you have a 4 kilogram object and its speed, initially its speed is 2 meters per second and 42 joule of mechanical work is performed on it. So please try that. I hope you have tried that, students. Then let's try to solve this together. What are the given quantities? Here we have 4 kilogram. 2 meters per second is the initial speed. 42 joule is mechanical work. Therefore, when you write the given quantities, these are the given entities or quantities. So we are asked to find the final speed of the object. The final speed of the object. Solution. From the concept of work energy theorem, work is equals to change of kinetic energy, which means work is equals to half mv final squared minus half mv initial squared. Change of kinetic energy means the final kinetic energy minus the initial kinetic energy. Therefore, when you substitute this, it's possible to rearrange this like this: work plus 1 over 2 mv